Now we are going to talk about experience-dependent plasticity in the developing brain. And we will briefly discuss a little bit later the work of Konrad Lorenz, who in the earlier 20th century started working with these geese, so gooselings. And with goslings, whenever they hatch, whatever they see first is basically like their caretaker, their mom, right, their dad. And so when Lorenz was hanging out with these geese after they hatched, they would think that he was like the parent. And what's the term for this? Do you guys know? Imprinting, yeah. So. Oh, that's so cool. Really? Oh my gosh, that's awesome. That's awesome. Well, I'm going to show you a video later of Konrad Lorenz, and I feel like this dude had like way too much time on his hands because like literally all he does is just like hangs out with his geese, which is cool. I mean, it's just living it up, you know, just living his best life. So it's super cool stuff. So these are all the things that we're going to talk about in experience-dependent plasticity. We're going to talk about Dr. Hebb's postulate of neurons that fire together, wire together. So Dr. Donald Olding Hebbs, who was a physiologist. So that was his main idea. We're going to talk about how things change as you develop from infancy into adulthood in terms of synaptic connections, because you see synaptic changes as you progress in maturation. We're going to discuss critical periods. Critical periods are the times during your development where certain types of skills are most important. Right? There's a critical period for the time when you really start learning how to see, vision. Critical periods for perception of sounds. Critical periods for a lot of different things. Even for like learning how to socialize and interact with other people. There's like critical periods for all that in terms of development. If you, for whatever reason, have those critical periods inhibited or damaged, then you're going to see permanent deficits in those skills, abilities, and even sensory perceptions. So we're going to talk about monocular deprivation, which has been done in like cats, for example. Well, they will like sew shut a kitten's eye during the critical period, and you'll see that even after opening the eye back up, the cat will never have vision in that eye again, at least to an adequate degree. And you can see that reflected in the regions that are responsible for processing vision within the occipital lobe. Then we're going to do a brief thing on Konrad Lorenz with his imprinting studies. I guess you could loosely say with studies. I think he was more of like a citizen scientist. He wasn't actually like formal, but super cool stuff regardless. We're going to talk about ADHD because ADHD does involve the development of the brain from a young age. You get some interesting patterns in gray matter development that affect the individual later on in life. We're going to talk about eye conditions, amblyopia, strabismus, where you have like a lazy eye and how that can have implications in your ability to see. And then we're going to briefly discuss retinal waves and oscillatory activity. And then we're going to, again, briefly discuss ion channels, neurotransmitters, neurotrophic factors, and things like that that are important for this type of experience-based learning. So to begin with, we've already kind of alluded to Dr. Hebb's postulate of neurons that fire together, wire together, and it holds true. The more connections that you have, the more stronger the connection, the longer that connection is going to continue on. Whereas if you don't have that connection, you know, being elicited enough, then it's eventually going to get pruned back. Right? It's like learning a skill. If you learn a skill as a kid, but you never use it again, it's going to be tough to learn that skill again, right? But if you do something for a prolonged period of time, you're going to get better and better at it, right? That's the whole entire process of learning. But long story short, weak connections are going to be degraded over time. So here's an example of Hebb's postulate in action. So these two inputs over here, these two neurons, those are the weaker of the two neurons. These three neurons up here, those are going to be the stronger of the neurons. And especially if they're firing in synchronicity, right? Their firing patterns are all going to be kind of linked up together, as opposed to the ones that are weaker. They're not firing in synchronicity. These ones are the ones that are going to remain, and they're going to continue to remain strong, right? That's going to establish a stronger synaptic connection. Whereas the other ones are eventually just going to dissipate. They're no longer going to be connected. And that's totally fine. You should not have too much excessive connection in your brain. It can lead to issues, right? You want to prune back those unnecessary connections. Activity of the presynaptic terminal and the postsynaptic neuron is highly correlated. And that absolutely falls in line with Hebb's postulate. Anything that's weak is eventually going to be eliminated, right? So the strongest connections are the ones that survive. And yeah, exactly. So little babies, they're exploring the environment around them, right? And it's important because when you get more exposure, more interactions with the environment, the exposure and interaction with the environment is what allows young kids to develop properly, right? And to reach full maturation. This has to do with language. This has to do with hearing. This has to do with all sorts of stuff. Seeing, even seeing is something that you need to have experience. You have to have exposure to. You have to have exposure to sight and stimuli from the environment to actually be able to strengthen those neurons within the occipital lobe. So really, really interesting stuff. If you change connections, you could see other connections coming in to compensate for that. Right? That's kind of like also the idea behind physical therapy. Right? If a person has an injury and maybe they get muscle damage, neuronal damage, you can start seeing plasticity coming into place. If you like try to train the person to regain certain lost functions, you can try to reestablish those connections. So other connections will help sometimes come in to compensate. Synaptic connections peak at 1 to 2 years of age. So infants and toddlers are going to have the most number of synaptic connections that they will for the rest of their lives. After 2 years of age, those connections slowly begin to get pruned back. And that's totally fine. So here are some MRI studies showing the brains of developing kids. Right? So you got a 2-week-old baby, right? Not as much gray matter going on at 2 weeks of age. So once you start getting into 1 year, then you get to 2 years of age, then you start seeing more increase in areas like the white matter. Did I say gray matter? I meant white matter. So you get more of the white matter type connections, right? Which are going to be like your tracts, for example. And those tracts eventually are going to peak out at a certain point. They're going to peak out at about 2 years of age. Similar thing happens to gray matter as well, right? So here's the total number of synapses. Here's the number of months of the individual. For this case, about 12 months of age, and then getting up to about 2 years of age, that's when you see a steady decline of those connections within the brain. So these studies were done on post-mortem samples. So an individual passed away at a young age, and they were able to go in there and take a look at the neuronal connections. So these are some Golgi-stained illustrations demonstrating that. So at birth, not really much going on in terms of synaptic connections. 2 years of age, look at that. It's like massive amounts of connections. So a huge web of synapses, which slowly declines as the years go on. So 6 years of age, not as many synaptic connections. Now, in terms of studies to see how sensory input is important, they've done, researchers have done all different types of experiments, including the monocular deprivation, where they literally go in, they sew the kitten's eyes shut, and they see how that affects the primary visual cortex, right, within the occipital lobe. So if they disrupt the inputs for sensory inputs, that's going to affect the brain. That's going to affect the way that synapses form. That's going to affect the development of neurons that are associated with those sensory processes. So here's monocular deprivation within a rodent. So you can do rodent studies as well. So they did monocular deprivation, and you can see that cortical territories are going to respond differently. So they did ipsilateral eye representation in a normal animal after monocular deprivation of the contralateral eye. So the contralateral eye, the opposite eye, developed more to compensate, right? Otherwise, both eyes generally develop simultaneously. And there's going to be a little bit of like competition between both eyes when they're developing in like the regions of the cortex. So you'll see like even distribution of those regions. But if you wipe out one eye, the opposite eye is going to overcompensate, and that eye is going to get more representation in the cortex, right? So the contralateral eye, the one that's not affected, would be the one that gets more representation on the brain. Auditory cortex is similar, right? If you play a certain type of tone, so for this case, they're playing an 8 kilohertz tone, prolonged period of time to this mouse or rat, and you can see that that region in the brain that corresponds to that specific range of frequencies gets increased, right? So the more stimulation you provide to the animal for that one type of stimulus, the more that area is going to develop in the brain. They did the same thing here with whiskers, right? They did expanded activation of certain whiskers, and you can see regions that are going to be corresponding more to, for example, in this example, they did C1, which is just one region of the brain that responds to certain whisker stimulation. Each whisker has different areas that are going to be represented in the brain. If you overstimulate that one whisker, that one area in the brain is going to expand, right? You're going to get more representation for that one whisker. Now, critical periods, again, are really important because those are the periods of time in development where you have to have established that pattern of like sensory processing. Otherwise, if you disturb that during the critical period, you are losing that forever. You're not going to get that again in the future. I mean, there's some ways that you can like circumvent that. We're going to talk about dark exposure when we in certain mouse models where they did wipe out the vision using monocular deprivation, but then they did dark exposure afterwards, and we're going to talk about that later. So dark exposure could maybe let the rodent regain some vision, but it's still not going to be perfect. It's not going to be like if they were just naturally learning a skill. So vision, right? Your visual inputs are going to have certain periods of your life that are really important for establishing those connections. Hearing, language, emotion, symbols, peer and social skills. Social skills, as you can see in this chart, it's about 3 to 4 years of age that this peaks out. Young kids, and this is based on some of Piaget's model of like childhood development. Young kids, if they don't properly socialize by the time they're like about 4 years of age, will probably never develop their social skills. And sometimes they'll even like become like institutionalized because of that. So young kids who are like facing abuse, maybe they're not being properly socialized, those kids are not going to grow up to have a good future, right? Because that critical period of like socialization has to happen within a certain period of time. Otherwise, they're not going to regain those skills. What's up?
Do you think this is going to become apparent in 20 years when the COVID babies all have social problems?
Oh God. That was like one of my biggest concerns, especially with like the whole mask thing, because like kids, like young kids, like when they learn how to like read language, part of it is also by looking at people's faces, facial expressions, right? And I feel like kids that grew up at that period of time, I think they're going to be emotionally blunted, especially in parts of the country that had like more and more intense like mask mandates, for example. I'm afraid that those kids are going to have some severe issues in development.
Social personality, like disorders and stuff? Like,
oh, I think so, because first of all, like there's a percentage of young kids. This is also like part of like Piaget's and like developmental psychology. Like there's a certain subset of kids who just like bite, they kick, they steal, they do like horrible things, but they're like young kids, right? And you have to train that out of the kid at a certain period of time. If you don't train that out of the kid and you don't socialize them within this period, right, like 3 to 4 years of age, that kid is not going to stop biting and stealing and kicking and being aggressive, right? Those kids are going to become like super antisocial personality when they're older. Yeah. So this stuff is important, right? You have to have like proper socialization development as a young kid. So That's all part of your critical periods. So that's a really good question. I thought about that a lot, especially during the height of all the shutdowns and stuff. I was like, dude, I'm curious to see what the long-term sequelae and consequences of this are. And there should be studies on it. It'd be really interesting to see what the studies might reveal. So here's imprinting. Imprinting is considered a built-in behavior, right? This is just like something that's innate in certain animals. And then Conrad Lorenz, this is this dude over here hanging out with his little geese. I mean, this guy just lived the life, man. It was so cool. He's just like swimming with geese. So interesting. Imprinting is a well-researched phenomenon within animals where they form an extremely close and dependent bond with the first animal they see after being born. So super cool. It happens in mammals and it happens in other types of animals. So here's another type of imprinting. So Harry Harlow did experiment with monkeys, right? And the monkeys preferred a soft cotton, like fake mom versus a like really cold, wiry metal mom, right? Because at least the soft, cottony fake mom kind of resembled what like a real mom would look like. And his experiments were done on rhesus monkeys.
Let me show you a monkey raised on a nursing wire mother. Now here are 106's two mothers. As you can see, it was weaned on a wire mother. Here's baby 106. Watch. He's going to the wire mother. Stop to eat the little. Going back. He's back on the cloth mother, and he'll stay on the cloth mother. Actually, this baby spends 17 to 18 hours a day on the cloth mother, less than 1 hour a day on the wire mother. We had predicted that the variable of contact comfort would be a variable of measurable importance, but we were unprepared to find that it completely overwhelmed and overshadowed all other variables.
Super cool stuff. Super cool. Super cute and super sad too. A poor little baby monkey. So that's part of imprinting as well. So again, babies preferred the cloth mom, even though they fed on the wire mom. So I'm going to show you guys a video later on. Oh, yeah, never mind. Sorry. It's right here. Let me play this video real quick because this is actually really cool too. I don't think there's any narration on it, if I remember correctly. But you can just see, like, the dude just had so much time on his hands. Basically, as far as I'm concerned, he's like the first one to basically do this. Anyways, let me fast forward it. There we go. Huh? Yeah. He's just living it up. So if you like read the comments on the YouTube page, it's like people are like, does this dude not have anything else to do with his life or his time? It's so funny. The Genghis Khan of geese. That's pretty good. I like that.
Working it really smart because they can tell the difference between my sister and me and my mom.
Oh, really? Yeah, I mean, bird brain, but they're actually pretty intelligent. So critical periods in the visual system. So over here, if you inject radioactive tracers, you can see how they go back to different regions of the cortex that are associated with that particular part of the retina. And so you can see which ganglion are going to be affected with like sensory exposure, right? Or even like deprivation as well. And there's a couple different areas within the optic tract. So there's the lateral geniculate nucleus, which is one of the regions that transmits visual signals all the way back to the occipital lobe. And there's different dominance columns. So these are all dominance columns. So this is in the lateral geniculate nucleus. And so different types of regions of the retina are going to be associated with different parts of the dominance columns. And it's a structure associated with the thalamus, the lateral geniculate nucleus. And again, really important in transmitting visual signals. So you get vision coming in from the retina to the optic nerve to the optic tracts. Lateral geniculate nucleus helps to kind of organize the visual inputs, and then that information gets sent all the way back to the cortex at the occipital lobe to be further processed, right? And so here are some examples of those like dominance columns that are associated with different parts of the visual system. So if you segregated the right and the left eyes, there's going to be kind of like it's like a zebra type pattern within the cortex that corresponds to those different eyes. And so they're usually going to be evenly split. You're going to have even distribution from left to right eye that maps out on the cortex itself. And if you were to do a monocular deprivation study, then that split is no longer going to be even, right? It's going to be a predominance of just one of the eyes, the one eye that's actually functioning properly. Again, this system is important for all sorts of sensory inputs, not just vision, but auditory as well, somatosensory, emotion, language. We're going to talk about language as well and the critical periods of language, which some very interesting studies that involved deaf kids that are born deaf, and their language is sign language. And there's a critical period for them to also learn sign language as well. So super interesting stuff. These are all the critical periods and different types of animals that were studied for these different critical periods. You guys need to remember every single one of these. I'm just kidding. There's a lot of different neurotransmitters involved in this, different animals, different systems. I'm not going to make you guys remember this, but it's a fun list that, you know, summarizes what's going on in terms of neurotransmitters. You see GABA is involved in this. You got NMDA with glutamate, right? You got acetylcholine coming into play. You got lots of different neurotransmitters involved here, as well as transcription factors like CREB, right? BDNF, right? Neurotrophic factors. All these things are going to be super important. So long story short, these processes are extremely complex, right? So it involves lots of moving parts. So now let's talk about language. Again, language and linguistic ability, it's optimal for young individuals to learn language at an earlier stage in their life, right? So linguistic experience begins with kids when they start babbling, right? Babbling is just like, you know, kind of incoherent words. They're just trying to produce words, and then oftentimes they'll mimic the actual movement of their parents' mouths when they're speaking. So I was listening to my colleague, Dr. Melillo, talking about when they were raising their kid, and mom is easier for young kids to say first than dad, because mom, they see the lips move with mom, whereas dad is the tongue moving, so they have a harder time seeing the tongue. And I was listening to, he was talking to his students about it. So when his kid learned mom, he taught the kid to say mom, and then he said bad. So the kid would say mom, bad, because that was easier for him to teach the kid. And I thought that was hilarious. So,
Whenever they say dad first, the moms are so pissed.
it's hilarious. That's funny. A good competition to have between like you and your spouse, right? Like, who does the kid like more? Obviously, dad. Anyways, example, deaf kids that can't speak or can't hear, right? Because hearing is important for speech as well. They're going to babble using their hands. And when they babble using their hands, you can direct that towards sign language, and eventually they can learn how to, speak with sign language. So I'll show you some of those experiments later on. And over time, language ability declines, right? That's why it's easier to learn a foreign language when you're a kid versus when you're older, right? When I learned how to speak Portuguese, I'm not like perfect at it, but if I were to try to learn Portuguese now at this stage in my life, I would suck at it. But I learned Portuguese because we would go visit my family in Brazil since I was a baby, since I was like 1, 2, 3. My Portuguese is fine. There's some words that I kind of struggle with, and some expressions that I struggle with. When I visit my family in Brazil, it like really comes back after like 2 weeks, and people are just like, "You have an interesting accent. Which part of Brazil are you from?" I'm like, "I'm a gringo." So like some people have actually thought that I was like either from maybe Argentina. Some people thought I was Argentinian because of I speak pretty well. But I learned Portuguese when I was 5 years old out of necessity because none of my family spoke English. I have like one cousin who speaks English so badly. He tries to practice with me. I'm just like, doesn't sound good. I'll stick to Portuguese with you. I learned French when I was in high school and in college, and je parle un peu de français, mais très mal. J'ai besoin beaucoup de pratiquer, which means I need to practice a lot. If I lived in France, I would probably be able to pick it up better. But if I learned French as a kid, I'd be speaking French way better as an adult. So there's like a critical period with language. Why does this happen? It's not super clear, but it's probably involving neuroplasticity, right? Young kids have more neuroplasticity when it comes to like language abilities. Can you learn languages in your adulthood? Absolutely. People do that all the time. They're going to be moving to a different country and they like start reading books, start taking classes, start learning the language. Are they going to sound like a native speaker? Probably not. They're not going to speak with an accent properly. They're not going to learn like all the nuances of the dialect. Yeah, way more effort. Yeah, kids are basically a sponge, right? They just soak things up from the environment. It's much harder when you're an adult. So again, babbling is the practice for children to speak. Deaf kids also babble with their hands and fingers. They did studies where deaf kids were raised by deaf parents that knew how to do sign language. And so those kids that were able to learn how to do sign language from their parents did really well. Deaf infants with signing parents, meaningful hand shapes increased as percentage of manual activity between ages 10 and 14 months. So they have basically a critical period for learning how to learn how to speak. Again, if you go beyond that critical period, your fluency is going to be affected. You have a decline in ability for learning a language. Like I said, you can still learn a language, but it steeply declines as you get older. So 3 to 7 years of age, that's definitely where you have the maximum ability to learn languages. So here's, they did some fMRIs on children versus adults. So they're doing like these visual word processing tasks. So there's a difference between the different regions of the adult versus the child brain where you have activation. So adult brains just function differently when it comes to things like word processing. So changes in either the circuitry or the motor processing and performing, right? That's where you see the difference between adults and kids. So you can see that on MRI. In terms of development and cortical synapses, again, like when you're young, you don't really have too many synapses, like the moment you're born, right? But then those synapses increase in numbers between the ages of like 1 to 2 years of age. And then over time, those synaptic connections steadily decline. Numbers of cortical synapses increase postnatally, then they decline over a protracted period, and then decline further into adulthood. You also have competition, right? Neurons are going to be competing for connections. Like I said, if you deprive one eye of vision during the critical period, the contralateral eye is going to have more real estate on the cortical regions associated with vision. So they're going to have more representation because they outcompeted the eye that was blocked with monocular deprivation. So here are studies done on rhesus monkeys between gestation and then 20 years of age. They did, it said rapid addition followed by gradual decline of synaptic density in the cerebral cortex. So let's see, here is, let's see, synaptic connections. So here's months. So these are like the critical regions where you have the most synaptic connections. So as you notice over here, these are, you have more and more synaptic connections, more and more synaptic connections, more and more synaptic connections, and they slowly decline over the years. And so this is motor cortex, prefrontal cortex, visual cortex, somatosensory, limbic system. So all the regions in your brain are going to have way more synaptic connections at a young age, and those slowly dissipate over time. And then here's the changes in gray matter versus white matter. There's also a discrepancy between males and females when it comes to this. This is no marker of differences in intelligence or IQ. There's just different numbers of synaptic connections between the two genders. But gray matter volume is going to change over time. And you see equal changes, right? Similar types of changes between the genders. Gray matter mass increases in volume and then over time decreases, right? Whereas with white matter volume, you're going to see white matter volume increasing throughout the period, right? So white matter connections, that's like, you know, your tracts, right? Myelinated regions of the brain. Whereas dendrites and synapses, right? That's where you see gray matter. Those types of synaptic connections decline over the years. And in this study, they were looking at the brains of 5 years old all the way to 20 years old. And this is for humans. And again, you see a steady decline of gray matter throughout the years, whereas white matter, in contrast, is going to go up over time. Now, in terms of clinical relevance, this could be clinically relevant in conditions like ADHD or attention deficit hyperactivity disorder. In ADHD, certain critical periods are going to be a little messed up in development. And so in ADHD, patients are going to have a postnatal increase in gray matter that is way slower. So gray matter increases, but not at the same pace as other individuals. So slow increase in gray matter. And you also see not just that, but you also see the gray matter beginning to diminish earlier on. So not only do you have slow growth, but you have early, basically premature diminishment of the gray matter. Now let's focus a little bit on ADHD as a disease. It's hard to call it a disease because, you know, people function with ADHD, right? They have to, you know, take meds. So many of my friends in med school had ADHD and they took their Vyvanse or their Adderall and they did great. As a matter of fact, my ADHD colleagues were some of the smartest kids I went to school with. Like, they were brilliant, and the Adderall really definitely helped. And sometimes I thought maybe I should have been on Adderall. Probably would have helped me a lot. These are the risk factors: genetics, right? Development, brain injury, alcohol and tobacco use in pregnancy can be a risk factor. Advanced paternal age. So the older the dad, the more likely the kid's going to develop ADHD. Low birth weight, premature babies. Things that don't cause ADHD: too much sugar, too much TV, poverty, bad parenting. These things aren't really linked to ADHD. It's other things. It's substances, chemicals that they're exposed to, genetics, brain injury, stuff like that. What are the symptoms? Trouble paying attention, daydreaming, extremely impulsive. Individuals with ADHD will think about something and they'll just do it right away. They'll do something without thinking about the consequences. So that's kind of like impulsivity. They fidget a lot. They forget things. They're chatty Cathys. They talk way too much. They have trouble taking turns, right? So if you're like sharing stories or if you're chatting with each other, right, they're going to always like try to interject. They're going to interrupt you constantly, right? They have a difficult time getting along with other people. This is total side note because I had a former student of mine who she has hypermobility. And she was like, is there a link between hypermobility and ADHD? Yes, there is. Why? I don't really know. It's, for whatever reason, you see neurodivergence when you see individuals with hypermobility. I have another student in my pathophysiology class who is like super double jointed. And he's like, I'm on Adderall, I have ADHD, and I'm hypermobile. I'm double jointed. And he was showing me like all the weird stuff he could do with his hands. And I'm like, dude, stop that. It's really freaking me out. It's wild. I mean, whatever the connection is, I don't know. But it could be just it's part of the genetic underlying or the underpinning genes that are involved in those processes. I don't know. This is the, if you were to do this in a clinical setting and try to diagnose someone with ADHD, this is the questionnaire. How often do you have trouble wrapping up the final details of a project? How often do you have difficulty getting things in order when you have to do a task that requires organization? How often do you forget appointments or obligations, right? So if a person's constantly running late, sometimes they might be unexpectedly rude. Maybe they flake out a lot. Maybe they lose track of their belongings and lose stuff all the time, right? These are all signs and symptoms of ADHD. How many of us in here have at least like some of these things? I have quite a few of these. I try not to be rude, but I definitely sometimes lose things. I have flaked out on things at times. I'm always running late. So, yeah.
You should do that on exam.
And I should do that on exam day. That's hilarious. And it's funny because I've done Vyvanse for when I was taking my board exam, and I found it extremely useful. It helped me rock my board exams. So Vyvanse definitely helped me once when I was taking it to concentrate. So when I was taking my board exam, the USMLE Step 2 is like notoriously difficult, and it's an 8-hour exam, and you're sitting there in front of a computer screen. And like when I took Vyvanse, I was just like zoning in. I could just hear my heartbeat, and I was like, this is awesome. And just rocking it.
Isn't that what Adderall does too?
Adderall does that for a lot of people, but it doesn't do that for me. I've tried Adderall before, and it didn't do anything for me. And then I've had people with ADHD say, that's probably because you have ADHD. And I wouldn't be surprised. I am a little scatterbrained at times. So, I don't know. I probably have like a subclinical ADHD, to be honest with you.
Ask you, like, I feel like, like 80% of people then probably have like a subclinical.
I think a lot of, like, we're all on a spectrum, right? It's a bell curve. I think we're all on a spectrum. You know, we all get bummed out every now and then. We all get anxious now and then. Does it mean that it's a diagnosable condition? No, not necessarily. But we all have these traits, you know. So here's the gray matter cortical regions as they increase. Gray matter volume increases more slowly in children with ADHD, right? The net result, lower gray matter volume in adulthood for individuals with ADHD. That's kind of the foundational stuff. Which lobe of the brain is the most important for ADHD? Yeah, the frontal lobe, absolutely. Yeah, that's one of the mechanisms of drugs like Adderall, right? What is Adderall? What's like the generic term for Adderall? For those of you who probably know someone or does take Adderall. If you look at your prescription vial, what does it say on that? Amphetamine salts. Adderall is literally meth. It's amphetamine. It's speed. And what it does is that it basically stimulates the frontal lobe. And what does the frontal lobe do? It allows for concentration, right? It also helps to filter out extraneous information so you don't get super distracted by stuff that doesn't matter, right? And so that's one of the mechanisms of drugs like Adderall, aka amphetamine salts. So that's why sometimes people abuse Adderall, right? It's a weird drug to abuse, but some people do it. I have buddies that like snort Adderall, right? They'll like pop Adderall when they go to a party and stuff. It's like, it's a weird drug to like party on. But, yeah. Does it take away your what? Oh yeah, it's an appetite suppressant. Oh, absolutely. Any of those stimulant drugs are going to reduce appetite. Absolutely. Cocaine, amphetamines, Adderall, Vyvanse. Yeah, all those drugs. So here is your monocular deprivation studies in the kittens, where they shut one eye and then they only allow the non-deprived eye to be stimulated, right? What And with a developing kitten, if you do that during the critical period, you ruin their eyesight. That kitten is no longer going to have eyesight in that one eye, or it's going to be markedly reduced. Now, if you did monocular deprivation in an adult cat, they've already went through their critical period. So if you do monocular deprivation, it's not going to affect the distribution of those, like, visual columns, right? It's not going to affect the visual cortex. You could see reduction activity. You could see reduction activity, but in terms of distribution, it's not going to affect the distribution of those visual patterns. So here's a couple studies that they used, that they conducted to test this, the monocular deprivation. So if you just look at the chart, I mean, this is normal, right? And then this is the distribution of cells that are activated. So contralateral, ipsilateral side. So in other words, contralateral side, that's when they shine the light into one eye, and you get part of the nerve fibers are going to go to the opposite side. Part of the nerve fibers are going to go to the same side. Remember, because you have decussation at the optic chiasm, right? And so some fibers stay on the one side, some fibers stay on the opposite side. So ipsilateral versus contralateral. And so when you shine the light in one of the eyes, you're going to see almost equal distribution from the ipsilateral to contralateral side. Now, this is where they deprived vision in the developing kitten during the critical period. They shut the eyelid, sewed it shut, and then once they open the eyelids again, after the critical period has passed, then they shine the light, and you're going to see absolutely no activity in the eye that was affected. You're only going to see activity on the opposite side of the brain. Versus adult, if you did the same thing to an adult after they pass their critical period, it will affect this. There will be diminished ability in those eyes, right? But it's not going to be completely wiped out because they already passed through the critical period. But you are going to see a decline in the ability of the eyes in the visual cortex. Now, this study in particular, they did it in certain days that really corresponded more so to the critical period. So here they did 3 days of monocular deprivation. So it was before 2 months, but it was after birth. And you saw some, pretty significant decline. If you did in that same time frame, but 6 days of monocular deprivation, you get really, really significant changes, right? So that's like right at that critical period, especially if it's, a longer period of time, like 6 days versus 3 days. So with monocular deprivation, you can also see studies like this in monkeys. So you see decreased column width, right? You get those like different columns that are corresponding to the different eyes. Short-term monocular deprivation, greatly decreased numbers of neuronal branches from the lateral geniculate nucleus. Long-term monocular deprivation was even worse, right? So this is time dependent. The more time you deprive those eyes to develop and the cortical regions to develop properly, the worse it gets. So these are some examples. This is short-term monocular deprivation versus long-term monocular deprivation. You get reduction in the branches, right? If it's for a long period of time, if it's for a really long period of time, it gets to a point where it doesn't matter anymore because you've basically just obliterated all those neuronal connections. So if it's for a really long time, the changes are basically going to start becoming equal. But if it's for a much shorter period of time, you're going to see changes, but it's not going to be as severe. And that being said, we're here. That's it. Yeah, I'll give you your umbrella back.
It's not right now.
It's not. Thanks, man. I really appreciate it. You're a lifesaver.
In the calendar, it says pre-topic 6 is due.
Yeah, it's chapters 9 through 13. Yeah. So do those, turn them in by Sunday. This is where we're going to continue next time. I'm like starting to fear that we might not. So I'm going to have to do some focus on like neuronal regeneration. I might not even put too many questions on the exam from that section because we haven't really covered it yet. I'm not going to test anything we haven't covered. So maybe we'll go over some high yield stuff because we're going to talk about Wallerian degeneration and like the reformation of a axon. So we'll go over maybe that process a little bit, But then everything else will just be extra information just for you to learn. I'm not going to test you on it. Rock and roll, guys. Have a wonderful spring break.
You too.
I'll see you when we get back.
I have an interesting thing to ask you about.
Yeah.
So
Yeah, see you later. Take
I
care.
had a conversation with one of my buddies yesterday, and he's texting me about it today. And he's not in like science, but he's very interested by stuff.
Uh-huh.
And he was kind of saying how like animals act out of instinct only, and I was like, that's not really true. They also act out of emotion. Like,
Yep.
Obviously, if you look at primates, they have plenty of emotional things.
Absolutely.
And then we started getting into it where he was like, well, how much of instincts? Because I was like, especially fear. This is also like, you know, kind of like just my thoughts. Doesn't mean it's correct, but I was like, oh, you know, I've heard that like animals act primarily out of fear for a lot of things too. Like that'll be a driving factor for an emotion.
Those are your your fundamental instincts. Take care, guys. You too.
See you,
Stay
Saj.
safe.
See ya.
Enjoy the wedding. Enjoy Mexico.
Yeah, I'll see you guys in Mexico.
I know. Are you going?
Yeah. But I won't be by you guys, but.